All right, we're going to look at measuring things in chemistry, measuring amounts. So far, we've been looking at molecules and compounds, and so we write a little equation, and we say sodium chloride reacts with, let's say, magnesium sulfate. Let's just write something here, SO4, there we go. And it's a double displacement reaction, let's say, so it's now sodium sulfate and magnesium chloride. And then we balance this, right? So we balance it by putting a 2 over here, and then that fixes everything up. And we talk about, twice as much sodium chloride being needed. We have twice as much of this as we have of this because of the 2. But how much are we measuring, right? The problem with chemistry is that these little molecules and compounds and atoms and things are all very, very, very tiny. And so, we could say, well, if we have 2 little molecules of NaCl, right, it's possible, I guess, that, let me just, this could mean you have 2 little NaCl compounds. Let's just put them like this, NaCl. And that would react with 1 of these magnesium sulfate compounds. And then if you shuffle the deck, right, then you could end up with 1 of these little sodium sulfate compounds, and then 1 of these magnesium chloride compounds. And if you look at the blocks, right, if you look at each piece, you pull these apart, and those 2 sodiums end up over here. There they are, right? And these 2 chlorines end up over here, Cl2, so they're covered. And then this magnesium here ends up over there. And then lastly, we have this sulfate over here, which ends up over there. So it all falls apart and reassembles itself, and it's all sort of accounted for. But the problem is, in real life, we can't just isolate 2 little compounds like this. They're too tiny, and they're not convenient to work with. So we need to be able to use a number or use some numbers that make more sense. When you're baking, for instance, when you see a recipe, you don't put in, 2 little pieces of salt. Usually they have measurements that are more convenient, like a cup of salt. Well, maybe not salt, a teaspoon of salt, right? A cup of flour, 2 cups of water. So with baking, we use not individual pieces of things like this, but we use things like a whole cup of this. So maybe we could say that this would be 2 cups of sodium chloride plus 1 cup of magnesium sulfate. And when you were done, you would make 1 cup of the sodium sulfate and 1 cup of magnesium chloride. We could do that, I suppose. But the problem is that the unit of a cup is actually not that convenient in chemistry either. We want a number, or we want a measuring thing that's going to be convenient for us to make things easy. Okay? I'll give you an example of numbers that are convenient, just so you understand where we're headed. If you look at, a dozen, we talked about this, that's 12 things, right? And you can have a dozen of anything. You can have a dozen cars, a dozen dogs, a dozen cats. But typically we use dozens for things like a dozen eggs, right? We buy eggs in a dozen, or a dozen donuts, or something like that. And the reason that we use 12 and not some other number is because 12 can be divided into many fractions that give us whole numbers, right? And we talked about how, if you have 1 dozen, that gives you 12 things, 12 eggs, right? 12 donuts. But if you only want a few donuts, you can have a half of a dozen, which gives you 6 donuts. And then you can do a third of a dozen, which gives you 4 donuts. You can do a quarter of a dozen, which gives you 3 donuts. You can do a sixth of a dozen, which would give you 2, right? Am I right? Yeah, a sixth of a dozen would give you 2. You could do a 12th of a dozen, which would give you 1. All right? And so you notice that when you do all these fractions, you get nice, easy whole numbers. Right? The problem with 10 is it doesn't work this well. Like if you did a third of 10, you would end up with, 3.33. It's not a very convenient number for dividing up donuts or eggs because you can't cut them into pieces very easily. So the dozen became a good way to sell certain things, especially things that we would like to, a dozen if you go to the baker and you want to buy some buns to get for supper. Well, you may not want 12, you might want 6, you might want 3, you might want 2, you might want 4. So you can get a convenient number out of this. So that's why a dozen is 12. Well, chemistry requires something like the dozen to make our lives easier. Now, of course, 12 is still nowhere near large enough to be able to handle molecules and tiny things. So a dozen doesn't do it for us. So what would do it for us? Well, it turns out that there was a very smart man, Emilio Avogadro, who was looking at the periodic table. And let's take nitrogen for an example. If you look at nitrogen, you'll see there's an atomic mass of 14. That's the atomic mass. 14 what? 14 kilograms? Obviously not for one tiny atom of nitrogen. One tiny atom of nitrogen is 14, and what we use is we use atomic mass units, which are very, very tiny, tiny little measurements, because we're talking about one tiny atom. So 14 atomic mass units, it's kind of like if you were measuring how far or how long something is, and you were measuring it in micrometers or really tiny, tiny little pieces. And so the 14 doesn't really help us much because we're not going to, if we were to measure out a bunch of nitrogen that we wanted to work with in the lab, we would have millions of these atomic mass units, right? It would be so heavy because we'd have millions of atoms. So here's what this guy figured out, Avogadro. He figured out that if you take a bunch of atoms and put them in a cup or a box, you can get just the right number of atoms. You can get just the right number of these nitrogen atoms so that the mass will now be 14 grams. So one atom is 14 tiny little units, but you should be able to get a whole bunch of them, and that would come out to 14 grams, which is something we can measure on a scale in the lab or whatever, right? We can measure grams. So he wondered, how many would that be? And it turns out that you need this many, 1.602 times 10 to the 23 atoms. And that would be then 14 grams of nitrogen. So that's a huge number, right? Scientific notation, that would be 2, 3, 4, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That many. Okay? So if we got a big box and we put that many into this box, right, tons and tons of nitrogen atoms, then we would find out that the mass of that would be 14 grams. And so why is this convenient? Well, it's convenient because the number 14 that we find here on the periodic table can be used two ways now. We can use that number 14 to describe the mass of one atom of nitrogen and say it's 14 tiny little mass units. Or we can gather up 6.02 times 10 to the 23 of these nitrogen atoms, right? I'll put nitrogens here. And it would be 14 grams. And so we don't have to change the periodic table. And so that's essentially what this number is. It's like the dozen of chemistry, except it's much bigger than 12. It's convenient. And we can measure 14 grams quite simply. He called this number the mole. Instead of a dozen, it's called a mole. And so a mole is simply 6.02 times 10 to the 23 anything. You can have a mole of nitrogen atoms, but you could also have a mole of people. If we could find this many people, there are not this many people in the world, but you could have a mole of ants, you could have a mole of oak leaves, a mole of cars. It's just that you'd have to have a heck of a lot of them, this many, in order to get a whole mole's worth. And so then, what that means is now we can go back to our little expression that we had before. Remember the sodium chloride and the magnesium sulfate, and it was becoming sodium sulfate. This is the same equation we had up above, and magnesium chloride. And we put a 2 here. So now when we read this, we can read it in two different ways. We could say that two little NaCl compounds, right? Two of them, which is very tiny. And then we could say one of these little guys, and we'll make one of those and one of those. Or we can now say, without changing anything, because of the magic of the mole number, 2 moles, and the short form for moles is MOL. For some reason, writing that extra E, I guess, was just too much for people. So MOL becomes the short form for mole. So 2 moles of NaCl, right? And 1 mole of magnesium sulfate, and you'll get 1 mole of this and 1 mole of that. And it's telling us the proportions. So this is easy for chemists to measure out. We get a cup, and we can put in lots of sodium chloride, and we can use our mole as a way of describing how much. And that's essentially what it is. When you get to grade 11 and further on, you'll learn more about this mole and how it works, how to do conversions, and how to do all the mathematics of it. We just want to know what it means for today, because we're going to use this to describe how much of something we have in a cup, right? We put in our beaker or whatever. We're going to use it to describe acids, in fact. So a mole is simply this many things, and it's a convenient number for measuring chemistry. And we'll stop there, and then we'll use this mole to describe the concentrations of acids and bases.